I hope everybody's enjoying their lunch in the second day of the conference. This afternoon we'll be joined by Chris Boshuizen, co-founder and chief technology officer of Planet Labs. Some of you know that in real life I write software for the Doves under Chris's leadership on the Spacecraft team. I have an immense amount of respect for Chris, who took a risk and left NASA with his co-founders Will and Robbie, and over only a few years has grown a small team of engineers in the Rainbow Mansion garage to a company of over 130 people and at least as many satellites. Please join me in welcoming Chris.
Thank you, Anna, for the invitation to speak here. So I have a question for you all, which is, who has seen this picture before? So I should ask, in this crowd, I should ask the opposite question, who hasn't seen this picture before? So of course, this is the blue marble picture, which was taken by the Apollo astronauts on the way to the moon in 1972 on Apollo 17. It's claimed by the NASA chief historian, Mike Gentry, that this picture is the most published picture in human history. And from the 1970s to the 1980s and onwards, this exact picture came to symbolize the green movement. And you can highlighting the fragility of the Earth, and became the poster child for environmental responsibility and climate change. So this picture was very inspiring to Will and I, but in a sense it represents the sort of pinnacle of old space. And this being the NewSpace conference, I thought I would talk today a little bit about how this picture and reflections on the aerospace industry at large led Will, Marshall, and I to be able to start Planet Labs and build some of the things that Hannah just described. So what was interesting about old space, I guess, was that it represented sort of a monumental triumph in system engineering. And particularly with the Apollo program, system engineering as we know it today is born. However, system engineering is, at this point, a 50-year-old discipline, perhaps, in the form that we know it. And there are other industries that are slightly newer that have different practices. So for instance, the software industry here north of Silicon Valley, between here and our office, uses different processes than what we would use typically at a NASA or large commercial space program. And so they have things called Agile, for instance, and sprint planning, and sprint dashboards, and 2-week release cycles. So two-week release cycles don't really seem to make sense in the context of aerospace. But to do what we wanted to do with Planet Labs, we needed to sort of really reimagine how to run a space company and try and move a little faster, be a little more lightweight, and get a little bit more done with fewer people and less money. So just a little bit about the company, where we are today. We founded in 2011. It was actually Christmas Day 2010, but if I say 2010, people had a year. So it was really, we didn't do anything really serious until after the holidays in 2011. We have 125 employees now, and a really thriving internship program of about 15 interns, including Hannah, which gets us up to about 140 people. We've raised $180 million in VC funding, including our Series C, which we closed finally at the end of March and April this year. And we originally started in Cupertino in a small garage, and we're now based downtown San Francisco. And we manufacture satellites there in our 2,500 square meter lab. So far, we've actually built and manufactured 100 satellites in that lab that we've delivered to space. And where's Rex? Rex visited the lab the other day and was counting how many satellites he saw in the lab scattered on people's desks, and got up to 58. So one of the cool things about building low-cost spacecraft is that you can give access to the hardware to the engineers. And so at Planet Labs, every engineer has a satellite on their desk, and multiple if they need them. So I'll talk a little bit more about that later, but I think it's kind of cool. So we've actually probably built now north of 200 satellites, fully functional, flight-ready satellites in our lab. And just this week, we deployed our 14 more satellites from the International Space Station. So, thank you. So what we want to do at Planet Labs is we want to image the whole world every day. We want to do that at reasonably high resolution, 3 meters if we can. And we want to do that because we think that the current satellite systems that are in space are inadequate to provide the needs for the people who need information to make judgments about their business, about stewarding the environment, looking after our people and our populations and our local ecosystems. So I think this was highlighted when the MH370 aircraft disappeared over a year and a half ago. I think most people were surprised that we didn't have persistent, space-based optical imaging of the entire planet 24/7. And here in this crowd, we know that's not true. We don't have that. And it's essentially that gap that we're trying to fill by providing persistent monitoring of the Earth. When we have our full operational fleet in space, we believe that we will be able to find and identify almost every natural disaster on the planet automatically, because we'll have an image of the day before, the day of, and the day after. And so we think that example highlights the sort of capacity that we want to bring to the world. So what's wrong with the current satellite systems? Satellites are fairly large. They're massive. Most imaging satellites are somewhere between 50 kilograms and 1,500 kilograms. And they're expensive, so there aren't too many of them. And so when they're in space, you have most satellite imagery is tasked. If you want to place an order, you pick up the phone, you make an order, you get the image back maybe 2 months later on a hard drive that was shipped to you, or on a DVD, or you pick it up via FTP. And so they're kind of like point-and-shoot cameras. Let's take a picture here, let's take a picture here. Sorry, it was cloudy, we'll try again tomorrow. Sorry, a high priority order from the president came in, we'll take another picture in a day or two. So it's rather slow. And so you have limited observations, and maybe you miss serendipitous events. And when something does happen that you found out about and you want to take a picture of it, you've got to go back and just start shooting everywhere, trying to take pictures. And it's kind of like a needle in a haystack problem. So you don't even know where to look. Plus, most satellites, because most companies only operate between 1 and 5 of them, have human-in-the-loop operations. So they have a small ops team that can run the sats, and they don't really need to scale. So scale is a key thing that we want to bring to the equation. So we need to change all of these. So the Planet Lab system is based on the idea of putting 125 satellites in a sun-synchronous orbit around the Earth. To date, we have 10 test satellites in SSO, and we have currently 24 active satellites in an ISS orbit for test purposes. And so what changes is you suddenly have always-on operations. With this fleet of satellites, you're able to actually treat them as a line scanner. And as the Earth rotates, you can take pictures every day. The data is fresh and persistent. Not, if you ignore clouds or take into account clouds, the freshest image is either a day old or maybe a week old in tropical regions or heavily clouded areas. And you can catch serendipitous events. So when something changes abruptly, you're able to find it. And if you have the right data tools, you can actually detect it automatically. Also, one of the important things is to operate 125 satellites. We can't have 5 operators per satellite. So we've had to invest very heavily in autonomous operations. So what you get as a result is you get this concept called Earth Observation Data as a Service. And so here in the Valley, we hear all the things like SaaS platform, software as a service, or PaaS, platforms as a service, or DaaS, data as a service. So we think that with this always-on capability, when you want an image, you no longer task a satellite. You request it from our database, and it's only a day old. In fact, it'll be the newest, most precious source of that data you can get. And so the concept of tasking actually goes away. The Planet Lab system is designed to have zero tasking capability, or as our investor Steve Jurvetson likes to say, it has infinite tasking capability. So that's the VC version of the story. So with infinite tasking, you can get an image of everywhere, anytime. So our operation system looks a little bit more like a cloud-based computer where the data is downloaded to our ground stations, put in the cloud, and then it's delivered to end users. So those users might be enterprise, they might be developers or scientists working in a lab, or it might even be users out in the field or at home using their mobile device to actually see something about their home, or their field, or their work. So that's sort of the ecosystem that we're trying to build. Hannah mentioned Dove satellites. This is a picture of one of the Doves. So this is a 3U CubeSat. It has deployable solar arrays. And it has the largest possible telescope that we could fit in the box. So our initial design problem was, how do you miniaturize a satellite that is typically the size of this table here, the podium in the front? Carrying the same size telescope, how do you miniaturize that down? And so most Earth observation satellites, and actually most satellites we've built to date in the history of this industry, have lots of boxes inside it. So there's a radio box, there's a computer box, there's a power system box, all kinds of boxes, a payload box. Those are all put together, and there's a lot of empty space or vacuum inside a satellite, a lot of free volume, and a lot of boxes. So we got a 3U CubeSat, and we filled 85% of it with a telescope. And so then our challenge was to fit the rest of the satellite in the remaining 15% of the volume. So that was the full power system, the control system, the radios, the computers, the payload storage. All of that had to fit in 0.15U of a CubeSat. And one of the miracles, I think, that enabled this was smartphones. And because I used to work on a project called PhoneSat, people think we have phones in the dogs. But that's not true. But it's the chips in phones that enable this kind of packaging. And so phones are kind of a miracle. They're not a miracle in terms of the hardware that they have inside them, because we've had GPS for a long time. We've had radios, we've had screens, we've had computers, we've had accelerometers. The miracle is that they all fit in a box that fits in your pocket. And billions of dollars of investment have gone into mobile devices. And so leveraging that investment and moving outside of the aerospace industry to other non-conventional supply chains allowed us to take brand new hardware, extremely high capability, very low power utilization, and fairly good robustness, and put it in a CubeSat. And when I was working on the PhoneSat project, we used to do things like we'd put phones on rockets, we'd buy them, shop them, we'd put them in vacuum. These were designed to be handled by extremely clumsy humans. And I'm sure you've all dropped your phone on a marble floor before, and it's been okay most of the time. So that's a 1000G shock. Phones are tough, and the hardware is designed to be dropped in a pool, to be used by us. So it actually is probably happier in space than it is in our pockets. So we took a risk and we built a satellite completely out of off-the-shelf components. In fact, this version of the satellite you see here in this picture is completely aerospace industry free. There's not a single component sourced from conventional aerospace supply chains. In the later versions, we upgraded the solar cells from silicon to gallium arsenide, so now we have one component sourced from the aerospace industry. The rest is all completely commercial, off-the-shelf hardware from regular supply chains like DigiKey and places like that. So just in terms of subsystems, in the interest of time, I'll skip through this a little quickly, but we have a lot of stuff in there. We have rechargeable batteries, we have 21 units in CubeSat speak of solar cells, we have a peak power point tracker, we have 2 variants of the solar cells that we can fly, we have a microprocessor that does our watchdog and housekeeping functions. We also have a web server. We have a full Intel Atom x86 web server running Ubuntu, which is the same configuration that almost all of the cloud computers in the Valley run on, with over ½ gigabyte of storage, which in old aerospace speak, in terms of our store and forward capability, actually gives us about 45 days of global capture per satellite that we can store before we actually need to download anything. And of course, we want to download it daily, but by moving to non-conventional supply chains, our capability is kind of off the charts in terms of what a regular satellite can do. I mean, this is 45 days of complete high-resolution 14-bit imagery that we can capture. We have our own radios. We developed our own radios in-house using chipsets available for mobile tech. So we have a UHF transceiver, and we have an 8.25 gigahertz expand down and a 2.1 megahertz, I think it's going to be gigahertz, sorry, expand up. So in terms of controls, we have 4 reaction wheels in a redundant tetrahedral arrangement. We have 3 magnetorquers. We have core sun sensors, magnetometers, rate gyros, star camera, horizon camera, GPS, it's only L1 band. And in terms of maneuvering, the one thing I didn't put in there was propulsion. And typically, if you add propulsion to a spacecraft, you almost double the complexity of the system. So we have not put propulsion in our dogs to date, but we do our orbital phasing and maneuvering using differential drag. And I know the Aerospace Corporation did some fantastic research 2 to 3 years ago doing relative differential drag of CubeSats, just using atmospheric drag and the drag coefficients of the solar panels in different aspect ratios to move the sats. So we've been doing that operationally, and we can actually maintain the complete accurate spacing of our satellite fleet using nothing but atmospheric drag. So this de-scoping propulsion was a very good choice. In terms of the imager, it's a Maxikov Cassegrain telescope. It's a 91mm aperture with a focal length of about 1.2 meters. Unlike most imaging sats, we don't use a linear push-broom sensor, but we actually have a 2D focal array, which allowed us to go and find really high-end industrial CCD cameras that we could use. So instead of sweeping and scanning, we actually just take pictures at 1 frame a second, copy those pictures to the hard drive, and then download them over the radios. So it's very much like a Linux-enabled webcam in space, just taking pictures, storing them in a directory, and copying them down. We also have a near-infrared option, so we're doing a tech demo this week, actually, in space of a brand new upgrade to the system, flying a near-infrared sensor, which is valuable for agriculture. And our ultimate resolution is a ground sampling distance of 2.9 meters from the International Space Station, and I think it's about 3.4 meters from our SSO orbit. And the GRD is about 5.8. So also this camera, the signal-to-noise ratio is about 80:1, and we have 12-bit images, and we provide ortho-rectified geotips with atmospheric correction for those imaging buffs. So it's a fully complete, backwards compatible data set that is a complete swap-in for any other image chain that you're using in your GIS processing toolchain. So whether you're using ArcGIS or GRASS or Esri-based products, our imagery is completely backwards compatible and has all of the metadata and information you need to do your processing. So our ideal constellation, as I mentioned, is about 125 sats in orbit at a 475-kilometer SSO orbit. And that kind of looks like this picture here. The Earth rotates west to east, and the satellites are spinning around, but they're fungible, so you can imagine them sitting still. And as the Earth spins, this is a giant line scanner, scanning the whole Earth 24/7. We don't have this many sats in a sun-synchronous orbit yet, but we will be launching those over the next year and a half or so. Right now we have 11 in SSO, 24 in ISS, and we're capturing about 3 million square kilometers a day from space. We also have 40 satellites that have just finished production in QA that are awaiting a launch later this year. In terms of ground infrastructure, we have our own UHF transceivers for doing telemetry and housekeeping, as well as a set of rented and planet-built, planet-owned ground stations, giving us a total network, I think, of about 30 antennas across the planet at the moment. So this is our ground network. Once the data is down, we need to process it and get it out to people. So we want to transform data how it's delivered by providing data as a service, as I mentioned. So that means building a whole bunch of web tools. When you're collecting, roughly 145 million square kilometers a day, as we will when we have our SSO constellation, you can't do any manual processing. It all has to be automatic, particularly if you want one-day latency. So whole world, 3-meter resolution, 145 million square kilometers a day. So we've had to build an automated pipeline that can ingest that imagery, rectify it, atmospherically correct it, adjust it for digital elevation models and other types of corrections that are standard in the industry, radiometrically correct it, and then publish it on a web API. So we have all of that right now, and we have a closed beta program running with our customers, with about 10 or 15 people who are actually trying this out. We're getting good feedback on the API and how the data looks, and we'll be shipping this product out to the rest of the world at a later date. Also, in terms of building satellites, another thing that we had to reconceive was what manufacturing, testing, and QA look like. And so when you're building large numbers of satellites, you can't deal with reworking a particular satellite. If you have one, it's fine. We've got a problem with the radio, let's swap it out, let's debug it. We have a manufacturing process, and we actually have end-of-line QA, much like a consumer device company. And so the satellites are mass-produced. When we have a delivery of, say, 30 that we want to ship to the International Space Station, we'll actually make 45, and we'll take the yield of the best 30 that we've manufactured, we'll ship those, and then we'll look at the last 15 and we'll test them exhaustively and find out why they didn't pass QA. And then we'll go back and we'll improve our design. Maybe we'll release a bug fix or improve a subsystem or take out a component and swap it for another one that's more reliable. And then we'll improve the design as we go. And so this idea of manufacturing and iteration and design cycles is really important to us. One of the cool things that the International Space Station opportunity provides is the ability to do relatively low-cost demonstrations and tech demos. So partnering with our friends at the International Space Station and our partners at NanoRacks, we've launched a large number of satellites, tech demos, and operational fleets off the ISS. And that has a really quick turnaround time so that we can iterate our design, manufacture the satellites. It takes us about, I think we can make one a day at the moment. So, within about 30 days, we can maybe send an entire shipment to the ISS. They'll sit on station and then they'll come out, and we can actually test our operations, test our mission control, test the hardware, get more feedback from space, and bring it back into the design. So we've always used space as part of our lab at Planet Labs, and it's an extension of our laboratory, and space is the highest fidelity simulation of space. And so instead of trying to build a lot of test stuff on the ground, we do it all in space. And we have basic, solar simulators to test our assumptions and measure our solar panels and do QA, but we don't do rigorous thermal analysis, and we don't do rigorous radiation design, and we don't do exhaustive testing on the ground and endless testing of edge cases. We build something, we launch it, we find out what broke, we fix it, and the things that didn't break we move on from. And so my engineers love this because they can get to sleep at night. If you're working on a 4-year mission and you've never launched it, and you're just waiting until the date goes, you have a lot of built-up anxiety. Okay, did I design the power system right? Is it going to break? What have I done wrong? Maybe I need to change this connector. Maybe the structure's not stiff enough. I've heard that one a lot. Let's stiffen the structure. And so you keep working on things because you're never really sure it's good enough. We were able to eradicate about 90% of our risks just by launching early, testing the SAT, and then moving on to the really important issues. And so that was one of the key things that enabled us to speed up. I really like the ISS launch. It's really cool. Normally when SATs are ejected directly from a rocket, you don't get to see this kind of footage. But these are the first 2 doves that we ever put in space from the space station. I like how they wink at us as they're disappearing. And this is another one of a later deployment from a different angle. And there it goes. And one of the cool things from launching the space station is the astronauts can take pictures. And this is a picture taken by Koichi Wakata, who assembled our first NanoRax dispenser in space and did the ejections for us. And he took this out of the window with his Nikon SLR camera. And I think it's really cool to get pictures like this, and we're very lucky to have this. So what's the result? We've got these satellites in space. What do you get? So I just wanted to show you some of the Planet Labs imagery. This is a Lake Turbog in Canada, and it's basically 2 alluvial plains and a glacier coming together with a lot of snow. And we've been watching this, and you can actually see very slowly things move and things fall off and break. And we have some great footage, not really footage, but stills over several days of actual movement and carving of ice off glaciers. It's really cool. This is the Patagonian Andes in Chile. And this picture is really neat because you can see the variation in the vegetation as over altitude. And so some of the sides of the hills are still shaded from the spring sun and haven't yet turned green, and the other sides are bright green. And so I think this is just a really neat example of a really beautiful ecosystem. In Japan, this is the Arakawa River in Tokyo, and I think this is a great example of the metropolitan scene. So you can resolve roads, you can see vehicles on roads, you can see buildings, you can see parks, you can see human activity. This one is the Chavamochic Special Project in Peru. And so this is a fairly arid region of land along the coast in Peru. And there's a massive water reclamation project there that is turning this into a viable region for agriculture. And one of the neat things that I've seen in our imagery that I didn't read anywhere else is that agriculture in the developing world is being radically transformed right now. And so typically, if you look at the US Midwest, you fly over it, you see lots of big circles. These are pivot irrigation things. So the US has fairly modern agricultural practices, and pivot irrigation is one of the staples of that industry. However, in Asia, Central Asia, Latin America, most farms have traditionally been run by small families, and so they're really small plots of land, narrow strips, owned by multiple people, farmed independently. But what we're seeing in our imagery is that those are slowly being replaced and consolidated with large pivot irrigation circles. And so this is not something that I read in the news, this is not something I heard about, this is something I discovered myself just by browsing around the data and comparing it to older images. And it's kind of shocking what the rate of growth of modern agriculture is in these areas. I was actually thinking about writing some software to count circles and give a daily graph of the number of period irrigation sites around the world, because it'd be pretty easy to do. But I think it's really fun looking at how things are changing. This is a picture from Inner Mongolia, and in a similar vein, sorry, moving too far forward. Some developing countries are moving rapidly into modern industrial eras, and in Mongolia that means installing coal-fired power plants. And so these are two new power plants in Mongolia. Inner Mongolia, just in northern China. And so this is a great example of the kind of data that you can see from space from our satellites. In particular, I can tell how many of the smokestacks are active, how much coal reserves they have out there. And we actually have images of almost every coal-fired power plant on the planet at this point. This is one of my favorite images. This is the Lower Sasan Dam in Cambodia. And so this picture was taken on December 24th last year, 2014. And so if you just look in the middle where there's that thing that's just about to cross the river, 30 days later, on January 24th, this dam section was almost complete. So this is quite remarkable. This is 30 days of work over our holidays. Building a new dam. This one is actually particularly controversial because this dam might actually impact the Mekong River and stop the natural flow of nutrients down to a lot of fishing areas. And there's grave concern that a lot of traditional Cambodian fishing areas are actually going to be destroyed by this dam. And so we're following this story really closely, and particularly downstream of this river, we're trying to collect as much data as we can to just ourselves understand what might be happening in that area and whether that claim is true or not. In terms of deforestation, this is some legal, not illegal, but legal logging in Oregon, in Corvallis. And if I just flip between these two images, this is the Landsat image, I think from May, and this is the planet image from September. And you can see, particularly on the bottom right and on the bottom left, large pieces of forest are now gone. So with this capability, we can monitor every forest on the planet. And it's my personal goal to count every tree on the planet and give them a name and keep track of them. And you can see this resolution, we can see trees, we can see tree canopies, and we can see when the trees are gone. In terms of agriculture and our data processing, these are two images from about 2 weeks apart in Sioux City, Iowa. And so a whole bunch of stuff changed before, after. And in terms of our ability to process this data and find things automatically, we're developing change detection tools. And so this is the change map of those two images. And so if I was interested in agricultural yields or concerned about food security, I could use this data to estimate harvest. So who's seen that movie, Eddie Murphy movie, Trading Places? So the whole story is about getting the crop report before the crop report comes out. So if you want it, come talk to me. And OJ features as well. So enabling factors that have led to this sort of kind of imagery and capacity is, as I mentioned, frequent access to space. So there's growing comfort with nanosatellites, and also regular supply to the International Space Station. Low-cost electronics, the Moore's law effects. Actually, our hard drive, now that we've gotten to 500 gigabytes, it's about, I wasn't paying attention, but we've been upgrading the thing every time a new version came out, and now we have 4 times what I thought the design capacity needed to be. So we're going to stop upgrading the hard drive and use Moore's law to see the price fall down exponentially as new versions come out. So we're hoping that will decrease the cost of our satellite, but we don't need any more storage. Massive investment in mobile computing has helped us. And in terms of optics, modern computers allow you to design and optimize optical systems and produce diffraction-limited, really high-resolution optics that fit in a really small package. And the innovations in web and cloud, in particular, helped us develop mapping frameworks. Google Maps didn't exist 10 years ago. And a lot of work has been done on how to distribute imagery online, how to use maps, how to browse things around. Cloud computing didn't exist, so we didn't have to build our own storage solution. So we've stood on the shoulders of a lot of work that other people have done. And most of this, I think the innovation at Planet has been to just actually stop and think and look around and see what's out there and put it together into a coherent story. So all of these innovations have been significantly helpful to us. I think most of us know what CubeSats are, so I'll sort of skip through most of this. But CubeSats are extremely useful, small form factors. I think perhaps 4 years ago or so, people thought they were toys. But our satellites and others in the industry have started to get capability that is on par with small sats. So CubeSats are now this new small sats, and I think femtosats or pocket sats are the new CubeSats. So watch out for those guys. But they're really cheap to launch, and they have over 10 years of history and several hundred have launched. So the CubeSat industry is here. It is actually quite large and very robust. In terms of orbital slots, I'd mentioned the SSO launches 52 degrees. We have one sat in 65 degree and it's geostationary. Geo is too hard for us. I mean, we make no claim that our satellites survive outside the radiation belts in the harsh radiation environment, GTO and beyond. But low Earth orbit, is very similar to Earth. Astronauts use their iPads on the space station, and their iPods and their laptops, and they work just fine. So low Earth orbit is a lot like Earth. And the SSO orbit, is ideal for our line scanner, but the 52-degree inclination orbit, people would normally think that's not a suitable orbit for Earth imagery. But most of the world's population actually lives between negative 52 and 52 degrees line of latitude. And with a large enough number of the satellites, you can account for the changing sun angles and actually collect enough imagery to build a really useful product. So by sort of ignoring conventional wisdom and putting sats in an ISS orbit, we've been able to actually collect and produce a really, really large data set of imagery, which is not something that I actually even necessarily believe was true myself 4 years ago. So the ISS orbit has been really valuable for us. In terms of our approach, I mentioned at the start this phrase, agile aerospace, and we iterate quite frequently. Normally when you build a satellite, you have one satellite, one rocket, you have one registration with the FCC, and it all really lines up really neatly. The launch is the launch of that satellite, the satellite name is the name on the application. We found, however, that because launches were slipping and we were iterating so fast, what we originally called Dove1 wasn't the Dove1 we launched. And Dove1 was actually Dove4, but the FCC application was called Dove1, and we couldn't change it, and the rocket thought we were delivering Dove1, but it was really Dove4 because Dove1s 2 and 3 were actually sitting on the shelf and were obsolete by the time the launch came around. So we decoupled our internal naming from the launches. And so, with approval from the FCC, we actually delivered a later generation of the satellite and got it approved for launch. And so our first 2 launches were actually what we started calling builds, build 4 and build 6, or generation 4, generation 6. So generations 1 through 3 never launched. Generation 5 we didn't finish because we liked 6 better. And then you can see on the bottom our rough cadence of developing different builds of the hardware. We now have build 13 in design, and so that's 13 builds in about just under 4 years, so roughly 3 to 4 months per build. And the launches, you can see our launch cadence there. Unfortunately, we had 2 failed launches, 26 satellites on the Antares at the end of last year, and 8 about 3 weeks ago on the SpaceX. But we still managed to launch a really large number of sats. And Flock 1E, the second last ISS launch, was inserted into space just this week. I mentioned manufacturing. This is a little bit of a view of our manufacturing line downtown SF. And one of the key things that has to change is this idea of QA and mass production. And so particularly for our batteries, launching on the space station, you have to take safety very carefully. And our batteries are extremely rigorously QA'd and batched and binned according to quality. And we launch only the highest quality battery packs on the space station. And so we've had to develop a full QA system that I don't think many other traditional aerospace companies need. So we really have mass production of batteries. We're actually take a lot of lessons from Tesla in how they handle their batteries and develop those. In terms of capability, I think this was one really neat graph. I was at SmallSat conference in 2013, and people were saying that they didn't believe that X-band radio was possible in a CubeSat. So actually that day we had, I think it was about 4 days earlier, we'd launched the sat into space with an X-band radio. And this is some of the data down from that satellite. I think the all-time record for data down from the CubeSat was, I think, RAX-2, which had 2 gigabyte downloaded total mission lifetime. In this graph, this is 3.5 gigabytes in a single pass over our X-band radio. So the units are 3,000 kilobytes, so 3.5 gigabytes. So you can see the link margin. We actually have a lot of extra link margin left. We could have actually pushed the encoding rate higher and got a lot more data off this. So our satellites are very definitively in the realm of extremely high capability, extremely robust Earth imaging satellites. And we have all of the technology to obtain and download a really large amount of data. This is the optical design. I like this. This Maxitop Cassegrain was developed in, I think, 1939. And it's 1/5 of the length of the focal length of the actual telescope. It's very compact, and it outclasses almost all other kinds of telescope. So this is the ideal telescope to put in the CubeSat. And it turns out that the sweet spot for crispness and resolution is when you have a 10 centimeter aperture, so 4 inches. So it's exactly the right size for a CubeSat. Our mission control is also a little different. Here's some examples of other mission controls. We've seen them all in movies and live feeds of launches and stuff. So you have SpaceX's Dragon mission control. You have JPL's Curiosity and JPL's Deep Space Ops. So what does our planets look like? It's actually just this really sad row of desks and a couple of screens for visitors. And so we have a giant clock. And actually, funny, all of the operators sit facing away from those screens. So they don't actually look at them. And so our entire mission control is on the cloud, and it's fully autonomous. We have scheduling algorithms that take into account the health of every satellite, their orbital passes, they propagate forward the TLEs, work out all of the access times, all of the camera windows, how much power they have. It all runs in a few seconds, schedules are sent up automatically, and our mission operations team is actually just a team of developers whose job it is to develop and maintain the code that runs that, but not to actually run the satellites. And I think you can't quite see it, but sitting down between the two monitors is Diana, who's actually one of our only 2 satellite operators, whose job it is to just sit and watch the sats to make sure that the mission control infrastructure is doing what we think it does, because it's still in development. But we're actually hoping in about 6 months from now to move those people out of an ops role and back into dev, because we don't think we need any human operators to maintain our entire fleet. This is a little bit what the dashboard looks like that we use. So we have all of the satellites, and you can see all of their key characteristics, what their statuses are. And so mission operations at Planet looks a lot like maintaining a server farm. In fact, we have an x86 web server with images that we download over secure FTP. It looks a lot like a web server. And so the concept of mission operations has been replaced with DevOps. And we maintain our satellites much like you would remote servers in a server farm. The only difference is our internet connection drops out for 80 minutes every 90. Other than that, it's essentially the same. So basic achievements so far. We've contacted every satellite launched. We contacted all but one on its first pass. That one had the antenna stuck and it didn't come up, and we were able to talk to it with a little more transmit power. We do continuous integration and deployment of software in space because we have an Ubuntu operating system. We send up operating system patches, we send up new packages, we update things. We can open a web browser on it if we want to. So we run the sats really like a software company. We maintain the spacing. We have continuous operations. And as I said before, 3 million square kilometers and 3.5 gigs of data per sat pass. So just to sort of close out, I wanted to just give one really neat example. So there was an earthquake in Nepal about a month or 2 ago. And one of our engineers, Erica Bilston, spent her Saturday and Sunday building a mosaic of Nepal with the latest data we had available and shipped it out to some of the aid groups. And we just, particularly as an Earth observation company, our licenses require us to distribute data to the US government to get to the other aid agencies. But we send this directly to some of the groups actually working on the ground in Nepal. And we didn't hear much back. And then maybe like 2 weeks later, they wrote this blog post about what they were doing. And it turns out with our data, and I've highlighted the key phrase up there on the side on the right, they were able to find 2 towns that were really sizable communities with lots of roads and lots of houses that only showed up on the vector maps as 2 street intersections. So it looked like 2 highways crossing, and people ignored it and were not sending any aid there. But the maps showed that there were entire townships at those road crossings that were not on the maps. And so these were also 2 towns that were in the area identified as high risk, and they were able to go out and see if they needed aid. And so this was sort of like the first really good example of Planet Labs data being useful exactly when it was needed. So I had this, is it playing? Let's skip it. So this, I just wanted to close on this. This is another picture taken by Scott Kelly on Monday from our first deployment of this set. And I think it's really neat because you can see the Earth actually resolved really well. And you can see the satellites. And I didn't think that this was actually possible. We have a video we created of an animation of what it would look like, and you can see the Earth and you can see the pictures, and it's actually uncanny because they're the same. And I hadn't realized that you would ever be able to see this much of the Earth and the satellites in focus like this. It almost looks fake. But what it says to me is that space is not as far away as you think. And that's all I had. Thank you. So we've got time for 2 or 3 questions. So first hand there in the suit.
It's a fantastic project. Fantastic project. But what I wanted to ask about was, do you get conjunctions in time to actually maneuver out of the way? And this is for the higher satellites, obviously.
Yeah.
And if you have your full constellation up there, what's the probability you're going to make the ISS dodge?
Yeah, so the first question was, can we deal with conjunctions in time? So the TLEs that were provided by JSPOC are not high enough quality, so we actually built our own network of ranging stations. So we have super high accuracy ephemeris for all of our satellites. We also have GPS on board, so whenever there is a conjunction notice, the first thing we do is run the GPS in super high accuracy mode and the ranging stations and get an ultra-fine orbit for the satellite. 95% of the time, that refined orbit puts us well outside of the error bounds of the conjunction, and we take no action. Probably, I think, twice so far in the company history, it's been a missed distance of maybe 300 meters or so after we've got the refined orbit, and so we've put the satellites in high drag and been able to extend it out to about 10 kilometers or so. So the response time, even in SSO, is pretty quick. In terms of the ISS, we will not be launching the full fleet at the ISS altitude. We'll be launching at 475 in a completely different plane. And for most of the lifetime of the fleet, we'll be nowhere near the space station. As the satellites finally get to end of life at about 4 to 5 years, they'll actually be spread across quite a range of altitudes, and they'll be deorbiting one at a time. And even right now from the ISS, even though they're launched within the space of a week, they actually deorbit across about a 6-week period. So our belief is that we'll be able to watch each satellite as it transits, and because it's in a different plane completely, most of the time the ISS won't be anywhere near there. In the sort of 1 in 10,000 chance that the ISS orbit does intersect with that orbit at that time, we'll be able to change drag and prevent that. We'll have full awareness of that situation up about 6 weeks ahead of time. So,
very good.
Thank you. In front there?
Yeah. Could you describe how the satellites get from the cargo capsule or the module to the deployment, that whole process?
Okay. So I normally have some slides on that, but I didn't put them in today. So the satellites are sent up on the resupply capsule as cargo. And they're usually packed 2 at a time in their dispensers, and the dispensers are modular. So it's kind of like a slightly longer peapod. And so on the station, those are assembled into a rack, usually about, I think, 2 by 4 satellites by 2, so it's like a big rack. that's loaded in the GEM airlock. And so then the Kibo robotic arm actually comes down through the open airlock, picks up the back of the pod and takes it out and points it down. And so then you saw in the video, you saw the robotic arm extended with the pod on the end. And then once that's in place, the commands are sent, the doors are opened, and the sats fall down. And last question up the back. Yeah.
What can you say to characterize your paying customers? Who is lining up to buy your product?
Great question. Yeah, so we have right now over 200 million in actual signed bookings. The industries that we're working with largely at the moment are agriculture, mining and resources, and forgotten the third one. Trevor? Okay, yeah. So typically large, mapping. Sorry, yeah. So people who wanted to build updated base maps and maps. So those are the three target verticals for us at the moment.
Thank you.
Great. So I think we should wrap up, or Hannah will kill me. So thanks, guys.